welcome. Please help me welcome Scott Sanderson and Joe Jevnik for their presentation, Playing with Python Bytecode.
Hey everybody, thank you all for coming out today. I know you are all really excited to see Scott and Joe come here and talk about playing with Python bytecode. Unfortunately, I have a little bit of bad news today. Scott and Joe actually couldn't make it. They just texted us saying they were involved in a freak scheduling accident. But right before they texted us, they also sent us their outline. So I know everyone here was really excited to learn about bytecode, so I'm going to try to do my best to give the talk in their place. So their outline said that they were going to talk about CPython's internal code representation. They were going to demonstrate some techniques for creating code objects from scratch, whatever that means. And they were going to show some techniques for manipulating and inspecting code objects and making code from new code. So I guess if this is going to be a talk, about manipulating functions in bytecode at runtime, we probably need some functions in bytecode to manipulate. So maybe we want to start with like a def, add a comma b, and just a very simple function, and we'll return a plus b, and we'll just call that and make sure that works. All right, so far so good. So I guess we've got a function here, and we want to somehow get at its bytecode. So everything that's sort of secret or interesting in CPython starts with a double underscore. So maybe we can try to find that here. So we've got dunder annotations, dunder call, dunder class, dunder closure. I don't see anything about bytecode, but we've got a dunder code. If I was going to put a code object on a function, dunder code is probably where I would put it. All right, so we've got a code object. So this is code at some memory address. It was created by file ipython input 6 gibberish. But we want bytecode here, so maybe we need to dig a little bit further. So we've got a whole bunch of attributes here. So we've got co-arg_count. So that's 2. So I guess co-arg_count is just the number of arguments to this function. How about, let's see, got co-selvars, co-consts. Yeah, well, maybe we'll try to figure out that together here. So co-consts on this, I guess, is just the constant or the tuple containing none. So maybe we'll figure out what that means a little bit later. Bytecode. Bytecode. All right. Well, there's a co-code here. And if we look at that, this is a byte string. So this is co-code. It's a bytes. My guess is this is probably the bytecode. So I guess the bytecode for add is pipe00, pipe1017s. I think that makes sense to everyone, right? All right, sweet. Okay, well, so this is a non-printing string, right? There's all these characters we can't see. So probably a better way to understand this is to just look at the raw integers in that bytes object. So, if we do list of add.dundercode.cocode, all right, there's definitely a little bit more structure here, right? So I've got 124.00, 124.10, 23.83. So, there's definitely kind of a repeating pattern here. So maybe the first 124 corresponds to the first variable, 124.1 corresponds to the second variable, and then 23 and 83 definitely means something. I was really thinking this might be a little bit easier. All right, you know what? I've got an idea. We're here. We're at PyCon. We're surrounded by some of the best, most knowledgeable programmers, who know about Python around. Surely there's someone here in the audience who's worked with bytecode, who understands bytecode, who maybe could come up and help me, teach everyone interactively about how bytecode is supposed to work. So is there anyone here who knows about bytecode or has worked with bytecode?
Well, I'm actually a PSF certified bytecode expert.
Well, ladies and gentlemen, we have a PSF certified bytecode expert here among us. Come up on stage. Can we get a microphone for him?
No need. I brought my own.
Wait, you brought your own microphone to somebody
Let's get back on track here. You had the right idea with that code object, but you're not going to get very far looking at it that way. Luckily, Python provides a module to help look at this. Why don't you try import this?
Okay, import this. All right, the Zen of Python by Tim Peters.
No, import dis with a D. It's the disassembly module.
Ah, okay, import dis. All right, I've imported dis. What do I do with dis?
We're going to call dis.dis of add.
All right, dis.dis of add. All right, well, that's definitely way better than just that list of integers. Maybe I'll put that back up there so we can see the difference. All right, well, can you tell us a little bit more about what this table means?
Sure. So while we have 8 bytes in our bytecode, we actually only have 4 instructions. We have a load fast, another load fast, a binary add, and a return value. So the 124.00 represents that first load fast. The 124.10 represents the second load fast. Then the 23 and 83 are the binary add and return value, respectively.
Okay, so 124.00 actually means load fast. Why does load fast take up 3 bytes in the bytecode when binary add and return value only take up 1?
Load fast says to load a local variable, but it needs to know which local variable to load. So the second 2 bytes there are the argument, which says which local variable we will be loading. The 124 is the opcode, and then 00 says load local variable 0. Then we have 124.10, which says load local variable 1.
Wait, we're loading 1 and 0? I thought we wanted to load A and B.
The argument is encoded as a 16-bit little endian integer, which is an index into an array of local variables. So this helps us out on the right by showing the numeric value of that argument, but that actually means we're going to load local variable A. Then on the second line, we will see that the numeric value of the argument is 1, but that actually means load local variable B.
Okay, so 124.00 represents load fast of 0, but that actually means load fast of A. Where exactly are we loading A and B to here?
Load instructions load variables to a shared stack so that they may be manipulated by other instructions later. As we can see, the binary add does not have an argument in the bytecode because it will just pop the top 2 values off the stack, add them together, and then push the result back onto the stack.
Okay, let me make sure I understand here. At the start of this function, we're going to have an empty stack. We're going to do a load fast of 0, which pushes A onto the stack. Then we're going to do a load fast of 1, which pushes B onto the stack. We're going to do a binary add, which will pop both values off the stack, add them together, and push the result back onto the stack. And then finally, we're going to execute a return value instruction, which will pop the top value off the stack and return it to the calling stack frame?
Exactly.
Okay, I think I understand the right-hand side of this table. How about this set of integers running down next to the instruction names? What do those mean?
Those are the bytecode offsets where those instructions appear. So of course, the first instruction starts at index 0. However, the second instruction starts at index 3 because indices 1 and 2 are occupied by the arguments to our load fast.
Okay, and then binary add is at index 6 because indices 4 and 5 hold the arguments to the second load fast. Okay, I think I understand that. What is this 2 up in the top left-hand corner here?
That's the line number in our source code where these instructions appear. This would be a little easier if we try to function with more than one line.
Okay, well, how about just def add with a sign, and we'll still do A and B, but then we'll do x equals A plus B, and then we'll return x. And then we'll do dis.dis of add with a sign. And okay, so what this says is the first 4 instructions of our code object correspond to the second line of our cell where we're doing x equals A plus B. And the last 2 instructions of the code object correspond to the third line of our cell where we're doing a return x.
Yeah, I think you're getting the hang of this. Why don't we try a function that's a little more difficult?
Okay, maybe like a absolute value function. So if we do def abs, take a single argument x, and then we'll say if x is greater than 0, we'll return x. Oops, return x. Else, we'll return negative x. And then we'll do dis.dis of abs. It's got a nice ring to it. Okay, I think I've got this one. So at the start of this function, we're going to do a load fast of 0, but that actually means load fast of x. Then we're going to do a load const of 1, so I guess that means there are different kinds of load instructions. We're going to do a load const of 1, but that actually means load the constant value 0. Then we're going to do a compare op of 4, which means greater than. How does CPython know that 4 means greater than?
Well, not all arguments are just some index into some array. Here, the argument is actually an enum representing which comparison we want to perform. So there are entries in this enum for all the comparison operators like greater than, less than, or equals.
Okay, and then after that, we're going to do
How about I take the next instruction? It's a little difficult. The pop jump if false does exactly what it says it will do. It pops the top value off the stack. If it's true, it continues execution like normal. However, if it's false, it will jump to the bytecode offset specified in this argument.
Okay, so if the result of compare op is truthy, we're just going to continue executing to the load fast at index 12. But if it's falsy, we're going to jump to the instruction at index 16.
If you see those arrows, that's Dis's hint to the non-experts that that instruction is a jump target.
Okay, let me make sure I can walk through this one more time. So if x is greater than 0, we're going to jump to these two instructions, execute a load fast and a return value. If it's less than 0, then we're going to do a load fast, then do a unary negative to negate x, and then return that value. It looks like there's two instructions at the bottom of this function that can never be hit. Why are those even here?
You're right. Those instructions are actually dead code. CPython has a pretty simple code generation algorithm. And one of the rules is that if a function doesn't end in a return statement, an implicit load const of none return value is added. So while it may appear like this function ends in a return because both branches end in a return, from CPython's perspective, this function actually ends in an if statement, so those dummy instructions will be added even though they can never be executed.
That seems kind of wasteful, don't you think?
Well, it's only 4 bytes, which is half a pointer. It's not really worth the added complexity to the compiler to remove them.
Okay, but say we really cared about those 4 bytes. Is there some way that we could remove them?
Well, you don't have to use the compiler to create a code object. You can just create one like any other object in Python.
Okay, well let's write our own abs function then.
Hold on there, killer. How about I start you off with a function a little more your speed? Maybe add 1?
Yeah, I feel like we could have done something a little more complicated than add 1, but fine. Okay, so if we're going to try to write add 1, we probably should write the Python equivalent so we know what we're trying to do. So I guess we're going to have add 1 of x, and this will just return x plus 1. Add 1 of 5 is 6. All right. Well, okay, so you just said that I can create a code object just like any other Python object. And any other Python object I construct by calling its type. So where do I find the type for a code object?
That would be the types module.
Okay, I guess that makes sense. And what am I importing from the types module?
Code type. It's the type of code.
All right, from types, import code type. And let's see what the docs say about code type. So we'll do print code type dot under doc. All right, okay, we got a billion arguments here. Arg count, only, all right, create a code object not for the faint of heart. All right, well, fortunately for us, we've got a bytecode expert here to guide us through this, so I guess we better get started. Well, all right, so we'll do my code equals code type. Well, arg count, that's just 1. We've only got 1 argument. Only arg count, I guess that's keyword only argument, so that's probably just 0. N locals, we've only got 1 local variable in this function, which is x, so that's probably just 1. Stack size, I'm going to throw this over to you, Mr. Bytecode expert. What is stack size?
Stack size tells Python how much space to allocate for variables on the stack. So we need enough slots to hold the maximum number of elements that will ever appear on the stack at any given time.
Okay, well, the largest the stack is ever going to be in this function is right before we execute the binary add, when we've got both x and 1 on the stack. So the stack size here should be 2. All right, next up we've got the flags argument. What are the flags?
Flags is a bit mask representing a set of various options this code object could have. There's a lot of these, so I went ahead and prepared some material ahead of time.
Wait, you prepared
Could you be so kind as to hit the down arrow on the keyboard?
Wait, how did you even get these
Let's
here?
get back on track here. The first flag here is co-optimized. This says that certain optimizations can be made when executing this code object. In practice, this means that this code object comes from a function and not a class body or a module. The next flag is co-new locals. This says that a new locals dictionary should be created every time we execute this code object. Again, this just means that it's a function and not a class or a module.
Okay, I'm guessing that co-var args means we take star args in our function, and co-var keywords says that we take star quargs.
Exactly. The next flag we care about is co-no-free. Co-no-free says that this code object does not share any variables with any other code objects through a closure.
All right, and then last up here we've got coroutine and co-iterable coroutine. What's the difference between a coroutine and an iterable coroutine?
These flags were added in Python 3.5 to support the async_def or types.coroutine decorator. So coroutine is set when a function is declared with async_def, but iterable coroutine is when a function is an old-style coroutine decorated with types.coroutine.
All right, well, yeah, there were definitely a lot of those flags. I guess we should try to get back to that original function, and there's more flags. Okay.
These are the flags enabled when you do a from future import statement. For example, from dunder future import division.
Okay, I think I've seen absolute import with statement, print function, Unicode literals. What's co-future bury as BDFL?
That says that the user has enabled enhanced inequality syntax.
Naturally. Okay, well, all right, I've got to imagine that's the last of the flags. So can we just get back to that function that I was running? Why did you reformat
You'll see
all
I've
of
selected the
this?
flags that we need here. Co-optimized, co-new locals, and co-no free.
I am so changing all of my passwords when this is over. Okay, so we've done arg count, quonly arg count, n locals, stack size, flags. Next up is code string, and I don't see anything else about bytecode, so I'm guessing this is our main event. So we're going to want a bytes, and then probably it's easiest to just write these as integers. So we need the actual opcodes for our bytecode. So what do we need here?
We will need 124.00, 100.00, 23.83.
Care to explain any of that for the rest of us here?
Yes. What this function needs to do is load x onto the stack, then load 1 onto the stack, perform a binary add to add them together, and then a return value to return this value to the caller. So we start with 124, which is the opcode for the load fast instruction. We only have one local variable, so we can store it at index 0. Next, we will emit 100, which is the opcode for the load const instruction. We only have one constant, so we can store that at index 0. Finally, we have 23 and 83, which are the opcodes for binary add and return value, as we saw earlier.
Okay, I guess that's not that bad. All right, next up we've got constants. Well, you just said we're only going to have one constant, so this is just the tuple containing 1 for our add 1. Now we've got names and var names. What's the difference between a name and a var name?
Names is a tuple containing the names of any global variables or attributes that will be referenced in this function. Since we don't have any, we can just use an empty tuple.
All right, one empty tuple coming right up.
The var names are the names of all of the local variables of this function. So this can just be the tuple containing the string x.
All right, got a tuple containing x.
The next 4 arguments don't really mean much if we create a code object from scratch like this. So the file name is the name of the file of source where this function came from. We don't have one, so you can pick your favorite string. Next is the name, which is the name of this code object. This should just be add1. Then we have the first line, though, which is the first line in the source file where this code object appears. This can just be your favorite integer. Finally, we have the lno tab, which stands for the line number table. This is a mapping between bytecode offsets to line offsets in the file. We don't have any lines, so this should just be an empty bytes object.
All right, I can do that. All right, and then last but not least, we've got the free vars and cell vars.
These are the names of any variables that we share with other code objects through a closure. Because we don't share any variables and we set co-no free, these both better be empty.
All right, 2 more empty tuples. All right, so that's all the arguments. So I guess if we call this thing, then we should have ourselves some executable code. So, all right, well, that didn't crash, so I guess we should try it, right? My code of 5, and this should give us. Hey, what gives? I thought you said you were some kind of bytecode expert.
We don't normally call code objects, do we? No, we work with function objects.
Okay, well, I bet you I know what you're going to say next, is that I can make a function object just like any other type in Python, which means I need to call its type, which means I need to get function type. So from types, import function type. All right, well, that worked well enough. Let's see what the docs say about function type. Function dot under doc. All right, this is way easier than the code object. So this says, create a function object from a code object in a dictionary. Well, I've got a code object, and I know how to make a dictionary, so I think we've got this one. All right, so I can do my add1 equals function type of my code and an empty dict. All right, that didn't crash. All right, moment of truth. My add1 of 5 gives me 6. All right, I guess we don't even need the CPython compiler anymore, but I suppose we should see if we generated the same thing. So let's do dis.dis of add1, and then we'll just print a separator to. So the add1 here is CPython's version, and then I'll do dis.dis of my add1 so we can see the difference. All right, well, load fast, load const, binary add return value, load fast, load const, binary add return value. Other than those nonsense line numbers, I think we've got exactly the same thing.
Well, not quite. you'll notice ours has a load const of 0, but the compiler gave us a load const of 1.
Hey, yeah, that's kind of interesting. Why is CPython's version doing a load const of 1? All right, well, we'll do print my add1 dot dundercode dot co-consts. All right, that's just our tuple containing 1. That's what we should expect. What did CPython generate? Add1 dot dundercode dot co-consts. All right, we've got none. And why is none in the co-const from CPython? Nothing uses none here.
That's just a quirk of the compiler. None will always be at index 0 for the co-const.
Wait, so are you saying that our handcrafted, artisanal, organic bytecode is actually more sleek and optimized than what CPython generates?
In a way that does not matter at all.
I mean, I don't know, that none, that could be the difference. Okay, wait a second. So if CPython is just looking up values out of this constants tuple, does that mean I can just switch that out on a function and change its behavior? Like, what happens if I do my add1 dot dundercode dot co-consts equals 2? Can I change my add1 into my add? Oh man.
Luckily, Python blocks these kinds of shenanigans. If you were able to execute that line, anyone who had a reference to my add1 just got a reference to my add2.
I mean, my add2 sounds great. I don't know why you wouldn't want that. Actually, I guess I can imagine some scenarios where you might want, numbers to stay the same. Okay. So if mutating code objects in place is a bad idea, does that mean there's no way for us to take a code object and turn it into something else?
Well, we can't mutate it in place, but we can always just make a new code object by copying all the attributes off our old one and changing any parameters.
Okay, so you're saying that what we need is like a function that performs a functional update on a function. All right, I think I can write that.
I also went ahead and wrote this one for you. It's a little complicated, save some time.
All right, so what you're saying this function does is it takes a function f and ** keywords, and what it does is grab the code off of the old f, and then constructs a new code object by copying all the attributes from the old code object, but overriding any attributes that were passed into this, and then wrapping that up in a new function type with all the other attributes of the function copied. So that means that I should be able to do update of, let me make sure I executed that. All right, you're saying that this means I should be able to do update of my add1 with co-consts equals 2, and this should give me a new function that instead of adding 1, adds 2. So this will be my add2. All right, still didn't crash. My add2 of 5. Bam, we get 7. I guess we're all well on our way to becoming bytecode experts too.
Well, that's cute and all, but you'll only get so far updating the metadata. The real meat is in that bytecode.
Okay, well, co-code is just another attribute of the bytecode, right? If I can update co-consts, I can just as well update co-code.
Now you're cooking with gas. Why don't we write a function that updates all the 23s with 20 in that co-code?
Wait, 23s and 20s?
Oh, binary add and binary multiply.
Okay, so you're saying that what we should write is like an def add to mul that's going to take a function, and then it'll grab its dundercode. So we'll do old equals f.dundercode.cocode. And then what we want to do is take this bytes object and replace all the 23 bytes with 20s, which should replace all the binary add instructions with binary multiplies. So we'll do new equals old.replace, and we'll do bytes of 23, and then bytes of 20. And then finally, I'm going to take that bytes object and wrap it back up in a new function. So I'm going to do return update of f with co-code equals new. And then if I do add to mul of my add2, all right, we didn't change the name, but if I do add to mul of my add2, then I should get my mul2. And if I call my mul2, move that up a little bit, of 5, I get 10.
See, bytecode hacking isn't so hard when you know how everything works.
You know, I think there's actually a bug in this generation algorithm you gave me.
Oh, no, I don't write bugs. How could there be a bug? All we did was replace the binary adds with binary multiplies.
Well, no. We replaced all the 23s with 20s. And you told me not a moment ago that not all the instructions in the byte, or not all the bytes in the bytecode are instructions. Some of them are arguments.
Yeah, but I mean, 23 means add, like, 23 is never going to be an argument, right?
Well, what if we had a function that had 23 local variables?
No one's going to write a function with 23 local variables.
Well, now that you mention it, I actually have a function. I actually have a function right here that takes 26 local variables. So this is my getX function. And you can pass it all the alphabet and it returns x. And x, in case you haven't noticed, is the 23rd letter of the alphabet. So if I do getX of star ASCII lowercase, which is just all the lowercase letters, then I get x. And I'm not doing any addition or multiplication or any fancy math stuff here. I'm just returning a value here. So add to mul should just be a no-op on getX, right?
Yeah.
But add to mul is going to replace all of the 23s with 20s, which means instead of loading the local variable at index 23, I'm going to load the local variable at index 20. And that means that add to mul of getX is going to turn it into getu. And now that I think about it, this actually could have been a lot worse. I mean, at least there was a local variable at index 20 for us to load here, right? I mean, what would have happened if we had, swapped out the index entirely so that it wasn't even a valid value in range? Like, say we did update of my add one, we just did co-consts equals an empty tuple. That would turn my add one into some sort of, like, bad one. And if I do bad one of 5, ooh.
Yeah. I think you segfaulted the interpreter there. Oh, now that I think about it, I think this bug also manifests in those jumps. We were just going to jump to the bytecode offset in that argument, but if that wasn't a valid instruction or out of range entirely, like, who knows what would happen?
Yeah, and now that I think about jumps a little bit more, those jumps are just, going to some particular offset into the bytecode, which means we could never insert or delete any instructions. We would change all those jump offsets. They would never work, right?
Yeah, we would need some way to recalculate all those jump offsets.
That seems like a lot of work.
Yeah.
This bytecode hacking thing feels harder than I thought.
Hey, didn't you say earlier that Joe and Scott had worked on a library to help with some of this?
Oh yeah, Code Transformer. I actually downloaded it right before the talk. I was thinking, maybe if we got far enough, we could look at it a little bit. Maybe they've got some ideas for how to solve some of these problems. So let's do from code transformer. All right, what do we got here? Code transformer. I guess that makes sense. There's a code transformer class. Decompiler, display, instructions, option, patterns, tests. They've got tests. Got transformers. Import. Oh, Joe and Scott implemented add to mul. I guess great minds really do think alike. All right. Well, let's see what's in add to mul here. Add to mul. Oh, it's a module. So I guess we should probably go try to look at the source for this. Okay. Well, add to mul. So add to mul is a transformer that replaces binary add instructions with binary multiply instructions. And it looks like what's happening here is we're doing from code transformer, import code transformer in pattern. And then from code transformer.instructions, we're importing binary add and binary multiply. So there must be some sort of instruction objects being used here. That seems a lot nicer than just memorizing 23 and 20 all over the place, right?
Maybe.
Okay, and then we're going to make a code transformer class. And we've got a method decorated with a pattern. So it looks like what's happening here is we're specifying patterns of instructions to match. And then we write generators that yield replacements for those instructions. So here what's happening is we're saying match the pattern binary add. And whenever we see that pattern, just yield a binary multiply as a replacement for it.
What's that steal method do?
Well, let's see. Through the magic of Emacs, we can find out. Steal says, steal the jump index off of inster. This makes anything that would have jumped to inster jump to this instruction instead. So I guess this is some technique for dealing with some of those jump resolution issues that we thought about a moment ago.
Yeah, that sounds a lot nicer.
Yeah.
You know, we built some interesting tools today, but they weren't particularly useful. Maybe there are some useful tools built into Code Transformer itself.
All right, well, let's see what we've got here. So we've got transformers, import, we've got as constants, byte array literals, decimal literals, frozen set, interpolated strings. All right, how about ordered dict literals? That sounds kind of interesting. So I think I actually read in the documentation that these are supposed to be used as decorators. So if I do ordered dict literals, and then I do def make dict, say take A, B, C, and then we'll do return A mapped to A, and B mapped to B, and C mapped to C. All right, and then if I call this, I'll do make dict of 1, 2, 3. Hey, look at that, I get an ordered dict instead of a regular dict. That's pretty neat. All right, let's see if we can find one more to go through here. Whoops. All right, we've got Haskell strings, or interpolated strings. I think this is for those of us who are too impatient to wait for the new f-strings feature in Python 3.6. So if I do @interpolated strings, and I do def inter, say we'll take an A and a B, and we'll just return a bytes that returns A and B. And if you're used to something like Ruby or languages that do string interpolation, I think what should happen here is, if I call that with 1, 2, it just magically gets interpolated into my string. So, I mean, I guess maybe there are some, non-insane uses for this. So I actually think that's just about all the time we have here. So to recap a little bit, I know you guys were all really excited to see Joe and Scott come out and talk about bytecode here today, but I hope, thank you to my bytecode expert friend for coming up on short notice with no planning whatsoever. And just to recap a little bit what we talked about today, we looked at CPython's internal code representation. We saw some techniques for constructing code objects from scratch. We looked at various ways that we could swap out attributes of code objects to change their behavior. But we also saw a lot of the dangers of playing God with the CPython compiler for ourselves. And maybe at the end here, we saw a few techniques for trying to mitigate some of those dangers. But yeah, again, I want to thank you all for coming out here, and hope you all have a great PyCon. We're okay. So, in case you guys haven't figured it out by now, I'm Scott.
I'm Joe.
We wrote a library called Code Transformer that's for doing this kind of bytecode manipulation. We think it's kind of a silly and whimsical topic, so we wanted to do a sort of silly and whimsical talk that went with that theme. In real life, when we're not doing things like this, we work at a company called Quantopian that builds tools for people to do algorithmic trading in Python. We do not use any of the techniques that you just saw there to trade other people's money.
Or anywhere else on the platform, for that matter.
You can find us both on GitHub. I'm github.com/ssanderson.
And I'm a barcode.
What Joe means by that is he's github.com/10 lowercase l's. And on Twitter, you can again find me at the reasonable name of @ssanderson.
And I'm Dunder Qualname.
So if we've got time to do questions, we'd be happy to take questions in whatever time we've got left.
Absolutely.
Thank you all.
Please raise your hand if you'd like to ask a question.
Got one down in the front here.
Hi, thanks for the awesome talk. Well, I have 2 questions. The first is, you said that this is only CPython specific, or is this the Python's model of functions and code?
No, yeah, so all of the bytecode stuff we saw here is very specific to CPython, and even down to minor versions of CPython. So the bytecode format is not in any way like standardized or guaranteed to be stable across versions. So bytecode from Python 3.4.2 to 3.4.3 would not even necessarily be the same.
I mean, I understand that the bytecode is not the same, but doesn't Jython, for example, have the same code model? Like
Well,
with
but
code
Jython's generating like
JVM.
Java, JVM bytecode.
Yeah.
It's a totally different format with totally different semantics. So like I don't think there even is a dis module in like Jython or PyPy, for example. Or if it does, it's just for compat.
All right. And my second question is, can you jump into the middle of the instructions?
Can you jump into the middle of an instruction?
Right.
So-
Like, if your
Wait.
instruction is 3 bytes, can you jump into the second byte?
The compiler does no validation on the bytecode at runtime, so it assumes that the compiler has generated sane code. You can feed anything you want there, and it will just run, but there's no guarantee that will do anything other than segfault.
Yeah, so you can, but almost certainly terrible things
Yeah.
will happen to your machine.
And just so people know, all of these examples were done on Python 3.5. Like, when we say that changes between versions, like 3.5 added new instructions. On 3.6 head of default right now, there's word code, which changes the size of all of these instructions. So this is truly an implementation detail.
Wait, you said 3.5, but you interpolate the string, you use the byte string and return a regular Unicode string?
Yes.
Pardon me, let's please raise your hand and have the microphone come to you so we can get that in the recording. Thanks. This young lady had a question.
The load fast instruction, it looked like it ended in, it was actually 3 bytes. And the last one was 0, so I was just wondering what that signified.
You're
So,
asking about
Like it's the 124, like 10 or 00?
Yeah.
So the 124 is the opcode, which says this instruction is a load fast, and it's going to load a local variable. And when it sees the 124 in the interpreter loop, it will then read the next 2 bytes as a short or a little endian integer, and it will use that to index into the fast locals, which is a field in an array, and use that to load a local variable out. So it's 10 because it's little endian and the least significant byte is first.
Do we want to get that question on microphone?
So you're saying you're working on Python 3.5, 3.6, what was it? Your interpolated strings, you used a bytecode object to return that, but the result you saw was a Unicode string.
Yes.
Yes.
Does it actually decode?
Yes, so I sort of glossed over this actually. You noticed that when I decorated that, I called it instead of just decorating directly. So one of the things that interpolated strings decorator does is say which, if I can get back, oh, there we go. It takes keyword arguments that say which kinds of string literals it should apply this to. So by default, it lets you use bytes, like byte strings as F strings rather than as Unicode strings. And you can pass a flag that says also do this for Unicode strings or don't use it for bytes. But it's really just using that as a signifier. And under the hood, this is essentially getting rewritten into something like the literal.decode utf8.format * locals.
Yeah. So we just use bytes because it's less common to see bytes literals than Unicode literals. So that's more of just a marker that says we're going to do something special with it.
Any more questions?
Got one here?
How many times did you guys go through this awesome talk and practice in your dry run?
We've probably rehearsed it start to finish 15, 20 times now, I would say. You know,
So I'm just wondering if you're familiar with kind of broader practical applications of this, like using it to write directly to hardware, or places where eliminating a few lines here and there actually could be useful, and if you know of anybody that's done that type of stuff.
Well, so in terms of practical applications, there aren't many because this is truly implementation specific and like no guarantees that any of this will work. I have seen some interesting things with a project called Pyrosite, which lets you hook into a running Python process and inject code. And someone had told me they were working on a project, I think it works totally, where they could hook a function at runtime to add breakpoints so that they could attach a breakpoint to a running server and then you'd hit a route and then it would hit their breakpoint. And then when they were done, they could just strip those breakpoints out, and there was no trace that they were there.
Yeah.
Yeah, you can.
As I say, that's sort of, we talk about like everyone who had an add 1 suddenly got an add 2. For something like I want to inject a debugger in there is actually a case where you might truly want to suddenly globally change everyone's behavior. Another example of something that's kind of in the same vein, although much more extreme than this, is there's a project in the numerical community from Continuum Analytics called Numba. And so here what we were doing was taking bytecode and sort of rewriting it into different bytecode. What Numba does is takes your bytecode and just throw it in the trash and replace it with LLVM intermediate representation so that you can, it takes your Python and tries to transliterate it into a much more low-level machine-specific language, and it's like NumPy aware and does some other fancy things. So that's sort of like the logical extreme of this if you're trying to do it for something like performance.
Other questions?
So if I was reading the example with a simple function and the load fast, it seems to mean that I can't have a function with more than 64K local variables. Is that right?
There's actually a pseudo instruction called extended arg, and it has an opcode followed by 2 arguments, and then that would precede an instruction that also took a short as its argument, and would merge those together to get a wider argument. So I believe those will be emitted for a load fast. I'm not positive. I haven't tried that. I'm sure Code Transformer has a test somewhere that does that. But
if you want to see some examples of like truly horrific code or strange code, look at the Code Transformer test suite.
yeah.
Other questions? Well, please help me thanking these guys for a great talk.